morning, everyone. Welcome to the Tuesday, January 7th community meeting, first one of 2025.
Happy New Year. Everyone doing okay? Good New Year. No one's missing any limbs or anything from the fireworks.
So far, so good.
Yeah, no one
But
regretting staying up late. I think I hit my bed at around 9 or 10. Uh, got woken up by a bunch of fireworks at midnight, of course. Fortunately, this year I did not have to run outside with a fire extinguisher for my neighbors, but
that's already a better year then.
yeah, yeah, it's a win, and I'm
There
glad
you
that
go.
that fire extinguisher around. Anyways, yes, as Chris said, welcome to our community meeting, January 7th, 2025. I guess we haven't had one in a while. It's been a few months. We had a pretty busy final quarter last year, what with reInvent and gosh, OpenSearch Con was in those final months, and then everyone going on vacation, not having a lot of presenters. So it was a slow final quarter as far as community meetings going, but I'm glad to see all 11 of us here, ready to rock and get things going. I think you'll not be surprised to hear us go over our etiquette. Please do introduce yourself before speaking so we know who we're talking to. Please do mute yourself unless you're actively speaking, just so there's no background noise. Cameras are optional. Questions anytime in the chat or audio, although I do like to include that if we have a presenter, let's adhere to their preferences so we're not interrupting their flow. And of course, if you're disruptive, we will kindly remove you from the meeting. We've taken several measures to ensure that things go smoothly here. No one can draw on the screen. We can't show profile pictures, just the name. Uh, Only hosts or co-hosts can share their screen, and passcodes are required and available in the weekly agenda. And of course, no renaming yourself to Nathan Boot and saying terrible, terrible things in the chat. So appreciate that. Everyone savvy so far?
Yep, let's
Have
go.
board? Wonderful. All right, some announcements. These ones are exciting. OpenSearchCon Europe 2025 is coming. I think you'll find that the process for which we accept CFPs and go through that grading process and results will go much smoother this year. We have the Linux Foundation handling a lot of that for us. And so, yeah, OpenSearchCon Europe, Amsterdam, April 30th through May 1st. It's going to be awesome. The CFP is now open. So please do submit any and all that you can. I'd love to see a big turnout. It always goes well, even if you don't think that your talk is very interesting. Any and all skill levels or technical depths are always welcome at OpenSearchCon. No one should ever feel left out. Anyone is welcome to submit a talk for that, and it will be welcomed with open arms. And we are indeed looking forward to seeing you there. Today's agenda, as you can see, Sam is here today. Sam Herman is going to be talking about Java and performance. Wow, CPU branching, memory allocation, and GC, isn't that the compiler? Uh, and then it looks like we will have an RFC to share for people's comments. Does anyone have anything for the good of the order before I hand it over to Samuel? I'm going to be trying to put forth more effort to have stuff to share, even if it's not from a guest speaker. I'll find little things to present. So we'll have more content to share, just to make these things a little bit more interesting going forward. I will do my best to entertain everyone as far as that goes. All right. Silence is golden, I guess, and I'll give it 10 seconds in case someone's a slow typer. Yeah. Okay. Well, I guess I will hand it over to Sam then.
Happy New Year, everyone. Uh, Great seeing you all. Um, I actually really excited to start this year with a topic that I actually kind of really enjoy, and this is about we're gonna be talking a lot about stuff from this RFC, but we kind of use it as like a learning opportunity. And a little bit about myself. I'm a TSC member, like the technical steering committee member, and as open source contributor. And okay, let's go. So in this RFC, it was kind of one of those things where I kind of submitted it as a bug, and then I thought, oh, actually, there's a bunch of places where we can use that. So let me make that into an RFC. And then I thought, oh, maybe a lot of people are like looking at this and they're like, what the hell does he want? So maybe we should just kind of make it as a teaching moment a little bit. So it helps the community to rationalize about what's in here, and hopefully it will be pretty handy, not just for this RFC, but for any future change you want to make in OpenSearch Core or in any other projects that are really important for you to get like really good performance out of your code. So I want to start with this. I draw a lot of like deep life inspiration from the best show ever, which is Peppa Pig. One of my kind of favorite episodes is where basically you have Grandpa Pig. He gets his new computer. His game is not working well. He's having severe data plane performance issues. Of course, it wasn't that specific, but that doesn't matter. And he called his grandkids and his kids, and they give him all kind of you know things to try, like power on the computer on and off. And then they're like, okay, grandpa, we'll come over, we'll fix it for you. By the time they arrive, they discover that he actually read the book how computers work, and he was able to get it to fix it himself. So the kind of cute moral of the story is that you should not be afraid, even if performance and all that stuff, data plane code sounds like a very arcane things. There are actually some pretty simple fundamentals behind it. We're gonna try to break it down. And once you have that, Grandpa Pig book of like how computers work, you're unstoppable. So do not worry about that. Will be great. So we'll all have to be a little bit of a Grandpa Pig after today, hopefully. One last kind of definition. You might hear me say things like hot path or data plane path when we're talking about OpenSearch code. What I'm really talking about is we're gonna differentiate between things, like repetitive code that happens many, many, many times, like a large number of times that can be unpredictable, such as the number of times a user can query, right, OpenSearch per second or for any time interval. And there are things that happen not very frequently, right? Like when we bootstrap, bootstrap OpenSearch, right? Or when we create a new index or change the index mapping, things like that are not very frequent. So we're not going to refer to those. So most of the examples that we're going to see here in these optimizations, they trade off, simplicity for complexity. And we're only going to do that on things that we consider hot path. Okay, so for the agenda, so we're going to start with example from the RFC, and we're going to talk about some aspects of it, of how we can potentially do better. and why we think we're going to do better, and how can we prove that this is actually better. So let's start with the first example. Actually, this one is the one that I bet if you go, you can find some more of those. I actually seen this piece of code for like, I think about 2 years ago, and I always wanted to do something about it, but I never actually had time to, but now is the time. So never, better late than never. So the in this piece of code, right, the place where it's at is, I don't know how many of you are aware, the remote storage path. When you try to, query a remote index, you're gonna have to fetch pieces of the index in blobs. And that depends on your, the size of each blob. So if, for example, we have k blobs that compose an index, and you're gonna have to pull all k blobs. So you're gonna have to send these k times that can be quite large, depending on the size of the index and the size of the blob. And also you can send those queries many times. So that definitely matches, and I would say even exceeds, the data plane kind of definition, this loose data plane definition we tried to provide earlier. So I thought it's a good candidate to discuss. So this is this piece of code, right? It happens every time, multiple times for each query. So let's take a quick look about that. So before we start talking about the first aspect, the first performance aspect that I want to talk about, it's really about the implications of dynamic memory allocation that are happening when we put a piece of code like that on a hot path. So just kind of, again, going back to how computers work kind of thing, when we think of memory management, we have something called the stack, right? And I bet many of you know it, but I'll just say it in any case, just so we're all on the same page, right? So there is a stack and there is the heap, right? And the stack is where we put the static, we have static memory allocation, things like local variables, or when we enter functions. So it's usually for things that we kind of know in advance. So if we define an integer, we know in advance that this integer is going to be 4 bytes, right? If we define an integer in a function. So we know that this is going to be stored in a stack in advance. Our compiler knows that. For things that we don't know, so if we take like a user input and then we're trying to create an array from that, then we're going to place that on the heap. It's kind of like an on-demand. And another interesting property is that, for the stack, it's kind of usually going downwards, so from the address space. So you see it starts with the high address, and the more you want to make the stack larger, you have to decrement the pointer. For the heap is the other way around. When we try to put something on the heap, like when we try to make the heap bigger or to allocate some memory to the heap, there is usually an operating system call called malloc. Okay, and we're gonna talk a lot about that in a bit, and what are the implications of that. Okay, so malloc, what is that? So in C code, it usually looks like that. So everything, regardless of whether we use Java or C or C++ or Rust or whatever, Ruby on Rails, when we try to create allocate dynamic memory, so whether when we create an object or array or whatever, this is something like that is what happening behind the scenes. So in this example, we're trying to create an array of 5 integers. So it kind of looks like this in C, where we say size of integer, this is how many bytes, and we call malloc and say, hey, give me this chunk of memory. store it in an integer pointer. And that's very, very ugly. Okay, so it looks very ugly. Luckily in Java, we don't need to make things this ugly, but we're gonna see here. So this is actually an example where, we take, the same ugly C code that we saw earlier. So if you wanted to do it in Java, it's gonna look like this, right? About that. And actually, what I want to show you here, I don't want to just go with you about code and say, hey, this is better than that. I really want us to quantitatively be able to evaluate. So one of the things I actually do is that I sometimes, when I'm not sure how things are going to perform, I actually translate them to assembly code. It's even uglier than the C code, obviously, but sometimes when I'm not sure, it actually gives me a bit of an idea of what's happening. So if we look at malloc, right? Actually, before we even look at that, why is assembly code good for me? Because if we remember how computers work, the thing that helps us really at the end of the day, when we try to say, hey, is this better performing than this piece of code than another piece of code? In the most simplistic way we can think about it, it's really about how many instructions our CPU take. If we have a single thread and we take instructions one by one, it's really about that. It's about taking instructions and spending CPU cycles. That's really all there is to it. So assembly code is a way for me to qualitatively evaluate this, because each one of these lines here is an actual CPU instruction, except line number 6, which we're going to see. So on the first, really when we look at this, it's like, oh, but just 10 instructions, not too bad. But no, line number 6 actually calls another procedure. So for malloc, you would see that we're actually calling another procedure. And what does that procedure do? So I actually looked what it does, so you don't have to do it. If you're really curious to see how malloc is implemented, it's you can like open this file there. It's thousands of C code lines. It's not pretty, which means potentially thousands of assembly instructions. The reason it's so complex is because unlike the stack, the heap can be fragmented when we free things up. And that means malloc has to do like a lot more checks. It has to be a lot more careful. And which is why it takes up a lot more CPU instructions. So definitely one of the things we need to be aware of is when we write code on the hot path that every time does like malloc or calloc or any kind of dynamic allocation, we need to be very aware of the actual cost it presents in terms of CPU cycles. So if we look at stack, so for example, here I created just an array that on the stack this is a kind of C++ format. That's practically free, because all we need to do in a stack is just decrement the pointer, and that's practically free. Unfortunately, we cannot do this in native Java language, so that is not available for us. So we're gonna have to find some solution. Okay, so one of the problems with malloc solutions, so the kind of first intuitive things we want to say is like, hey, let's go and create a buffer, right? Like, let's kind of create a pool, right? So we don't have to do a malloc, right? But that doesn't really automatically solve our problem. And the reason for that is that, let's think about it. So if we're going to start creating a pool, what is the pool? What is the size of each thing in the pool going to be? Say the pool will have pages, right? And then it's going to also be fragmented, and we're going to have to free and release and manage that stuff. What did we do? We didn't do much. We tried to really reinvent malloc on ourselves. that is not necessarily a guaranteed improvement. What we actually can do, right? Oh, this was actually an animation. I did not know that. Okay, so what we actually can do is we can take the example of a circular buffer. So we can try and reproduce actually something like the stack that we don't have like in Java natively. And in that approach, we have like kind of a pool, but if we know that say every element that we're creating has the same size, then we know that in this pool, right, we're always allocating things of similar sizes, and all we need to do is to increment a buffer. And when we're done with it, we can decrement it. This is really kind of something similar. It's to the stack, and it's actually used a lot in kernels and kind of databases, and it's actually used quite a lot, that technique. And this is something we can do for request or payload that is always the same. And we don't want to really create, to do dynamic allocations every time or write ourselves code that will reproduce this complicated logic. Okay, so summary about dynamic allocation. So if we're doing this on the not hot path, we don't care. If it makes our code clear, we don't care. But if we do things on the hot path, it's quite expensive. It's discouraged. We need to try not to do that. We cannot have stack allocation in Java. Pool of objects does not necessarily make things better unless we don't do dynamic allocation, which is why our workaround is when we know that when we have fixed length or fixed sizes for memory chunks that we want to allocate, we can use techniques of circular buffer to overcome that. Okay, so that was the first part of memory management, is really the cost of dynamic allocation, just the pure instruction cost. There is a softer cost too. And that cost, again, we're starting with very hard costs that are like, hey, this is the number of instructions. And as this presentation goes, you can see that there's like softer costs too that are not strictly just performance or yes or no performance. They're also about qualitatively impacting our project. So the next one I want to talk about is garbage collection, is GC. So what is GC? What is it good for? It's really for lazy people like myself that do not want to remember when we need to. So after we do some dynamic allocation of memory, we don't want to remember that, oh, we need to release this memory. We want to write sloppy, irresponsible code. And because I love doing that, it's like really the best thing to do because it allows me to do other things that I like more. But in this case, you can see when we created the array here in Java, we did not have to think about freeing it. And unlike here in C or C++, where we're gonna have to remember, hey, we have to free, this segment of memory back to the heap. Otherwise, it's like lost forever until we run out of memory and we crash and burn. So this sounds really good. Like, what is the problem with that? I mean, why make people work hard? I kind of like being lazy. And the reality of this is that I just did a quick Google search, and the first example is from Cassandra. The second one will be from OpenSearch, do not worry. But the immediate implication of that is that someone really had to work hard and think how we garbage collect all this stuff that Sam creates in his code. We've, and how do we collect that and feed that? So while I was lazy, someone had to do something that will work after me. That thing is a garbage collector. And this garbage collector has every once in a while do some extra work of going through all the objects, see which one of them are no longer referenced, release them. And that takes resources from our, from our CPU, from our program. And if you see, for example, one of the implications of that is that it's also it can be very unpredictable. And what we don't like is unpredictability when it comes to performance. So you can see in this example, for example, someone complaining that, hey, I'm trying to run this thing, and then all of a sudden everything just freezes. I cannot even log in or accept new connections. Everything is stuck. I don't know why. I haven't done anything. What's going on? So this is a common kind of, it used to be a common pattern. Of course, GC have gone a long way. People did all kind of smart things. But we still see that. Even I just took a quick search and OpenSearch here. And even for OpenSearch, we see all kind of weird, interesting things where we trusted this smart GC algorithm with one JDK and then something changed in a different JDK. And you can see this long thread about, hey, which flag might be missing? And it's really not very difficult to miss flags when it comes to garbage collections. There are actually multiple ways you can optimize it and multiple ways you can tune it. And there's like a ton of complexity that it really adds on operations and operationally analyzing performance. Even if eventually it will all be good, still just the sheer amount of complexity of understanding, why things are the way they are, it's quite a bit. So some kind of summary of GC is like the first implication, really, the things that if we are to summarize most of the complaints, let's say even if we made it perform with the same throughput, there is a latency variance for every query. Our users don't like to have one query take same amount, say a certain amount of time, and a few minutes later, the same query takes, I don't know, 10x amount of time. That is not showing a consistent experience to the user. It adds a lot more operationally on the engineer. Again, and this is why I said this is a soft cost as opposed to like a pure, say, instructions cost, as we saw with the malloc. Okay, so then what do we really want? So if you look at the RFC, so again, it's analyzing this chunk of code, and it's warning like, hey, we actually, every time we create new object here, we're actually creating the potential. It's not only that it's expensive in terms of instructions for malloc and dynamic allocation, it also means later GC, unpredictable performance. We don't like that. So there is the suggestion there again to use a buffer pool, because if we avoid the dynamic allocation and we know when we want to release the memory back, then there is going to be no GC, no garbage collection activity. And this is really what the RFC is proposing, those two main problems at the core. Okay, so again, just again to summarize, we favor latency over throughput. So even if you tell me, hey, like I have this GC thing and average, all the queries will be running at the same speed. It doesn't matter. We want predictability. It's important for databases, which are interactive systems. The best solution to achieve that is to avoid GC in the first place. Again, there is a trade-off here. Obviously, writing a code like this and doing all that cool stuff, it adds complexity. Sometimes it's worth it. Many times it's not. When it's like a critical hot path thing, it's one of those things where it's worth considering. And yeah, and again, we're going to try and use finite fixed length pools, so we don't really create GC or some other weird thing that kind of defeats the purpose. Okay, so the last thing I want to talk about in terms of performance and really kind of soft performance implications, when we look at this, this is and the two things before were more general. This one is really more specific to builder pattern. I want to talk a little bit about CPU branching and the overhead of builder pattern, especially when you put it in the hot path like that. By the way, I did not say this earlier. Please do not do a git blame on this because I really don't care. This is a teaching moment. This is none of that stuff. It's just a really good example. So this is why I keep putting it on and on. So just make that part clear. But the builder pattern, and I'm sure it's very cool. It's very it's very clear. It's much nicer. Because when you do a constructor, it might be less clear which argument goes to what parameter. So I understand there is a lot of clarity benefits to builder pattern. Again, when we're talking about data plane, there is a trade-off with performance, and we need to understand that when we use builder pattern on the hot path. So the builder actually has a bunch of overhead. And the first overhead, I don't know if you guys can see it, but when you do this dot builder thing method, you actually create a new builder object. So you already created an object, and then each one of those things that you add here. So you do this dot blob parts that returns the builder object again. So you actually call a method and then another method that returns the object and then another method. So you called here like 1, 2, 3, 4, 5 methods, and you created one object and a second object. And then each one of those you copied from the first object to the second object. So all those things create overhead, and we're going to try and evaluate what this overhead means in terms of performance. So let's look at just the overhead of a method call, right? So again, breaking it down to assembly. So let's say I have function 1, function 2, and function 3. So function 3 is inlined, and function 2 just calls function 1 that does the same thing without inlining. And what you can see here is you can see for function 1, this is really kind of all the instructions that we need for function 1. But for function 2, you can see that it's doing, for each entry to a function, you see that we have to increment and push and do all these manipulations on the registers for the stack. And that's actually can be expensive. Another thing you can see here that the compiler actually, when it looked at 2 times 2, it did it not only inlined, it actually pre-processed the result and it just put like a 4 here. So using constants actually also helpful, but this is less relevant. What I really want you to see is the entrance to each method. There is a cost there. Another cost that is a bit more soft that you might have not seen in the previous example is the cost of CPU branching. What does that mean? So when I go in from this function, right, when I say call, when I enter function 2 and I call function 1, I can potentially create a CPU branch. What does this mean? So CPUs, they usually work as a pipeline. So they take not just one instruction at a time, but they already kind of prep the next instructions they start pre-processing some of the next instructions on the pipeline. Now, those instructions, our CPU usually assumes it's sequential. And if there's suddenly we are kind of changing to some other place, we create what's something called a bubble, and we break the pipeline. So we make it less efficient, potentially less efficient. Now, of course, this is not always true because first, the very smart people that build CPU in an amazing way, and they learn to do all kind of things called CPU predictions. Branching predictions. Sometimes it works, sometimes it doesn't. That helps. That can help many times with CPU branching. The other things are that compilers became way better, and they can help with CPU branching. Although the GCC 14 compiler I used in the previous example did not do such a great job with that. The other things that so we already talked about those costs earlier, right? Those costs are like hard costs, right? The object creation, the method call, the field copy. But there are actually some very fascinating research that was done by just-in-time compilers where they actually profile the code, and they also do some predictive branching. So there are all kind of things. So one might argue and say, hey, you know what, like, fine, I mess up some things here. I may be messing this up, but I'm not really sure if this makes a lot of any difference at all. And then that's a legitimate feedback, especially with kind of state-of-the-art researchers like this for GraalVM. So one of the very nice tools you can do is you can just use JMH. And in OpenSearch, we have some of those micro benchmarks. So JMH is a micro benchmark where you can write, you don't want to really run the whole OpenSearch benchmark. It's quite slow. You want to only benchmark kind of a specific piece of the code. And you can check, for example, here, I just try to check whether the branching optimization is really working to such a great satisfaction. So when I used random data, I could actually see a noticeable difference. So this is, again, if we assume something smart always happens, then the answer is no. When we're not sure and we think that the trade-off is too great with the clarity of the code, then JMH is our best friend. Okay, so yeah, and if you want to be, again, a little bit more of a grandpa pig, you can use all these amazing flags to see how your compiler or just-in-time compiler is doing all the different optimizations. And that's if you're just, kind of a curious and somewhat bored individual, like myself, you can take a look at those. And yeah, and kind of, again, just kind of circle back is really, I would just kind of as a rule of thumb, I would recommend to avoid builder pattern on the hot path. for both the all the overhead that we described earlier for object copying, object creation. Um, it's a redundant object creation, object copying, and the multiple method call creations. Um, there's some manual performance optimizations we can do there. There's going to be trade-off with readability. Lots of fascinating algorithm things exist today to optimize things like CPU branching. So if we're not sure if those are actually helpful, JMH. That's it. Any questions?
Yeah, I think it was an excellent talk. I think a lot of people just go ahead and code, and I think don't have the time to look into the low-level details about performance and how the how all of this gets processed. So I think there are a lot of artifacts over here, and I think you brought up quite a few comparisons between native code and architectures and Java over here, and I think that's of course a good point. The malloc stuff was obviously on the dot, but one point I was raising was most low level allocators go at a higher level, right? I mean, C++ uses new, and I mean, even malloc, I think nowadays you've got tmalloc and other malloc allocators, which really operate with a pool allocation. You talked about circular buffers, but people might go ahead and do a binary. I mean, you might have different pools for different sizes and different users, and which it increase the efficiencies. On the Java side, I think it's absolutely right that there's if you lose sight of how the garbage collector works, you end up in issues. There are aspects of how garbage collection works. I mean, there's also the pauseless allocator like Azul has, with a read barrier and so on. So I mean, where you don't have a stop the world and you don't have that big penalty that you pay with certain queries. That was one point. And I think I do agree that taking control of how allocation actually happens, with your own pool in Java, and not randomly relying upon the garbage allocator, definitely will be a big help. But at the same time, it comes with the downside of trying to manage that as well, right? I mean, when you take control of a big pool and you want to allocate out of that, then you need to deallocate it too, and so you end up with the same issues that C++ also has. So at a certain point, I think something like Rust or so on, which has a different methodology, might be a good place which tries to overcome many of these aspects of how collection also happens. And finally, yeah, I think branches and so on is also, it's also a good point. The CPUs nowadays have got pretty sophisticated branch prediction. Again, that's native code. And then if you can assist it, I think that's great. But at some point, you need to sort of know how those branch prediction algorithms do work. So yeah, that was a mouthful, but a great talk. Thanks.
Oh, thank you. So I think just kind of one thing, like I would say a couple of things I would just say here. I think I definitely acknowledge the point of like, hey, you go, 2025 and trying to redo a lot of like, definitely we don't want to try to reinvent a malloc or garbage collection ourselves. This will defeat the purpose. And I also second what you say. Yeah, if you try to do a lot of those fixed length buffers, and now that can make some inefficiencies too. So all those definitely. One important point I want to make here is we really try to not do it everywhere. So we don't have many hot paths in the code. Usually we have a few of those. And when we get to those hot paths, this is where we really have to be very mindful. And that's kind of the high level point I was trying to convey. I hope that came the right way, but thank you very much for that feedback.
Yeah, I absolutely agree. I mean, it pays. I mean, generally, when you deal with performance or you look at optimizations, you want to focus on the core. Or, I mean, yeah, as you said, the hot path is the right term to use in that regard. So, so focusing on how that happens and how we optimize that um, is definitely very useful, and I think worth probing in detail. I think especially the things that happen again and again, and the way allocation happens over there, anything that you can do, like the builder pattern and so on that you mentioned, I think would be good for all developers to keep in mind.
Cool. Thank you very much.
One other hand raised, and
Okay.
this is a 5-minute warning that we're coming up on the hour, so we might have to
Okay.
officially cut things short. But I think anyone who has the time is welcome to stick around. I'm not going anywhere.
Yeah, Dimitri had their hand up.
Dimitri?
Well, yeah, you know me, we work together at Oracle and OCI. So yeah, we had that fun experiments with Lucene. So it's not quite open source Elasticsearch. It was just a pure Lucene and ingestion engine. We tried to squeeze maximum performance out of it. So just sharing 2 experiments that we did together actually. So one is I actually tried to do document arena so that when you ingest a document, you want to reuse all the buffers as much as possible. So like next document comes and you reuse some previous document, including all the classes of Lucene. The problem is that when I tried that, I didn't get any performance improvements because based on my analysis is that working with strings in JVM, internally it's already circular buffer or arena already in JVM. So as we know that Lucene has in heap memory and out of heap memory. So the trick is that when the buffer crosses the boundary of being out of heap to in the heap, it's already, when it's inside of the heap, the string buffers, it's already kind of inside of JVM. It tries to reuse memory as much as possible. It's already arena. So trying to make another arena on top of existing arena doesn't give any improvements. That was my one of the experiment learnings. At the same time, there was also good good use case of performance improvements when I completely removed all Java patterns and rewrote in C++ style the ingestion. So it was pretty much one big static function, and everything happened inside of one function. So without creating new classes, everything. It was one static and it was calling other static functions. So that actually improved like 2 or 3 times performance of the ingestion. But that code was hard to maintain. It was, imagine, like 2,000 lines of code of just like parsing stuff, everything in place without creating long-lived objects. So that actually helps. It makes sense in some places to do like that, to not follow Java patterns, do old-fashioned C. And but yeah, it will be hard to maintain that. Otherwise, yeah, it's a good old principles that works. Yeah, thanks.
This is actually very good. These are very good comments, actually, that come from past experience. Those are always the best, I guess, more than we can produce with JMH at this point.
I want to point out Andre has put a link to a intense looking book in the chat. So if you want to dive even deeper, we can always count on Andre for diving super deep on topics and providing the fodder for everyone else to do so as well, along with Mr. Sam here. We Thank you both. Thank you, everyone. Thank you,
Thank
especially
you.
Sam, for showing up and showing everyone this presentation. Super insightful. Nate, do you want to close
Um,
us out?
Yeah.
Nate,
I
I
guess
see
we're.
you also had the question, Nate, about what you mean
Oh,
by hot bath.
yeah. I actually Googled my own answer to that, and it's something I should have instinctually known because like there's certain sequences of code that get executed over and over and over, or very frequently, and that's when you're optimizing a project. That's usually what you go for. If you're going for like time complexity optimizations, or even just down to the byte kinds of optimizations. So uh yeah, I was just, for some reason, it didn't quite come instinctually to me, but I Googled it, and so we're all good.
Okay. Cool.
But anyways, we are at 9 a.m. today. uh I'll go ahead and close us out, but is there anything short, or anything that we can get through really quickly for the good of the order? Does anyone have any like quick announcements or anything?
Just one more reminder, everyone, go submit your CFPs for OpenSearchCon Europe and go register. We love to see you there.
That's kind of what I was hinting at there. And just a quick notice: if you have some ideas and you need someone to help flesh out a proposal to put in, or if you're nervous to get on stage, or if you need any kind of encouragement or technical tutelage, that's what we're here for. I'm sure I'm happy to help, and Chris is happy to help, and if anyone on the
Yes,
team is not able to, we will find someone who can help you if you want to get involved in our convention.
absolutely.
And that's how we build a community.
Thanks,
Awesome.
everyone, for helping us kick us off for the new year, and see you around. Take care.